So now in this last part of an introduction to trigonometry is where I want to make the connection between the right triangles and the unit circle. And some textbooks will actually go the reverse direction. They'll teach the unit circle first. It all just depends. I personally tend to stick with the right triangles for most everything. But I do want to show the connection here. So something we've already kind of talked about is that the adjacent side is the same as the x value and the opposite side is the same as the y value. What's different is with the unit circle is that the radius is always 1. So that means that the hypotenuse is always 1. And so let's say we take something that we already know. So if we take our 45, 45, 90 triangle, we said that's 1, 1, and square root of 2. Well, that's a similar triangle, and if I drew that on here, it would be, bigger than that original triangle, but it would be similar triangles. And so what's happening for the unit circle is everything gets scaled so that the hypotenuse is equal to 1. And what we could do here is to get that, we could actually divide the hypotenuse by square root of 2, and then we could do the same thing for the other sides as well, to keep it consistent, to make sure that it's still going to be a similar triangle. So then that triangle becomes 1, and then 1 over square root of 2 is the same as square root of 2 over 2. And then 1 over square root of 2 here is the same as square root of 2 over 2. So similar triangles, it's just the one with the hypotenuse of 1 would be one that falls specifically on that unit circle. Okay, I want to show a few different animations before I look at the rest of these notes. Okay, first I want to show this connection here, which is really just trying to show you that even when we're dealing with the unit circle, that connection between the right triangles and the unit circle. And here it's not even specifying that it is the unit circle, but I don't think I can change it. But basically the comparison is that the radius of the circle is the same as the hypotenuse of the right triangle. Okay, here's another animation that it shows the same idea, but I know that this is the unit circle because that hypotenuse of the triangle is equal to 1, which is the radius of the circle. And so one thing is, if I drag it around, one thing I just want you to see is this comparison between, if you've been looking at it from the right triangle perspective, the adjacent side is the same as the x value, and the opposite side is the same as the y value. All right, let's look at another animation. Usually when people talk about the unit circle, they not only talk about a circle with a radius 1, but they actually also talk about a circle that shows all the values for those special angles. And so here I just kind of want to show you one at a time first. So let's say if we look at 30 degrees first, because it's been scaled where the hypotenuse is 1, essentially the x value becomes cosine and the y value becomes sine. And then if I go to, but it still refers to that same triangle that we did in an earlier video. Here's 45 degrees and 60 degrees. So those are the three main angles in the first quadrant. And I can actually drag this around and do the same thing in all the quadrants. But even if you try to memorize the unit circle, I would not recommend memorizing the whole thing. All you need to do is know that first quadrant, and then you use what you know about reference angles and when the x's and y's are positive and negative to get the other values. And here I'm going to click Show All to show you what the completed unit circle looks like. All right, in this animation, I want to just show you that idea of, the unit circle means that the radius is equal to 1, so it looks something like this. And then you can rotate around and you could create a little triangle in there to get all your different values. But it actually works for a circle of any size, just which is kind of the same idea of similar triangles. So I can make that radius bigger. And you'll notice, yeah, we're still dealing in here with the angle of 55 degrees. The hypotenuse is different, the opposite's different, the adjacent's different, but when you actually looked at the ratios, they would still be the exact same for that angle of 55 degrees. Okay, here's another animation that I wanted to show you. So I've got the hypotenuse at 1, so that's right now equivalent to a unit circle. We're dealing with a reference angle of 35 degrees here, so it's not one of our special angles. But what I want to show you is it shows you the red, the green, the blue as the length for the opposite, adjacent, and hypotenuse, and it also has the values for sine and cosine. So one thing I want to show is that if that hypotenuse gets bigger, so this is again the similar triangles idea, I want you to see that the lengths of all the sides of the triangles are changing, but not sine, cosine, tangent. That's what I'm talking about when I say that the ratios don't change. The same thing happens when I go down as well, to shrink all of those lengths. And it doesn't matter what angle we're dealing with. The values for sine, cosine, and tangent are going to change, but it doesn't matter if we're dealing with a bigger or a smaller right triangle or a bigger or a smaller circle. If you're trying to evaluate trig functions based on the unit circle, this is just showing the same thing that we've talked about already, which is that when you would expect the trig functions to be positive or negative. Okay, so for me, I typically will use right triangles for pretty much everything that I do in trigonometry. Really the only place that I think about the unit circle is when I'm trying to find an angle that's a quadrant angle. So 0 degrees, 90 degrees, 180 degrees, and so on. You technically can do them with right triangles. It just looks a little bit weird. Like for example, for 0 degrees, if I tried to draw like a little maybe fake right triangle in here, if it's on 0 degrees, what that means is that I can make my hypotenuse 1, but this doesn't actually rise up at all, so it would be 0, and then that would be a 1. So it's kind of like I'm taking a line that goes from the origin 0 just straight over to the right on the x-axis, but I'm trying to make it look like a triangle because it doesn't have any elevation. The y value is 0. But if I draw my triangle like this, I can use what I know about the trig definitions from the right triangles to get the value. So sine is opposite over hypotenuse, so that's going to be 0 over 1, which is 0. I could do cosine, which is adjacent over opposite, 1 over 1, which is 1, and I could also use the fact that tangent is opposite over adjacent. So let me go ahead and erase this. But I could do the same thing if I just keep in mind that I'll just draw a point. I can just draw a point over there on the x-axis and think, okay, that ordered pair I know would be 1, 0, and use my definitions from there, knowing that when I'm using the unit circle, the hypotenuse is always 1. And so in this case, I'd say sine is just the y value, which is 0, cosine is just the x value, which is 1, and tangent is y over x, which is still 0. What happens for 90 degrees? Well, one more time I'll draw the triangle and then I'll just move just to the points only. So if you want to try and make a triangle to represent that 90 degrees, again, you have to use your imagination a little bit here because this is technically at 90 degrees. It's just like I'm trying to stretch it out to the right just to try and visualize it as a triangle in standard position from what we have done. But this adjacent would now be a 0 because it's technically not there. It's like up where the regular 90-degree angle is. This would be 1 and then this would be 1. So sine of pi over 2 would be opposite over hypotenuse, 1 over 1, which is 1. Cosine of pi over 2 would be adjacent or x, 0 over 1, which is 0. Tangent would be opposite over adjacent. So 1 over 0, which is undefined. Okay, so I realize though that triangle looks a little strange there. So I might recommend instead thinking about it in terms of the unit circle. So if I put a point up here, if I put a point up on the positive y-axis, that ordered pair would be 0, 1. Sine is going to be opposite, which is the same as y. So that's going to be 1. Oops, I already wrote it down anyway. A sine is going to be opposite or y, which is 1. Cosine is going to be x, which is 0. Tangent is going to be y over x, which is undefined. Okay, you could do the same thing for the rest of these. I'm going to go ahead and just look at the unit circle instead. So for pi, we could use the ordered pair -1, 0. So sine would be 0, cosine -1, and tangent would be 0 over -1, which is 0. For 3 pi over 2, we could use the ordered pair 0, -1. So sine would be -1, cosine is 0, and tangent is -1 over 0, so it's undefined again. And then if we look at 1 full rotation, 2 pi, that goes back to being the exact same thing as what it was for 0, which is 0, 1, and 0. And one thing to note, which does happen with angles on the quadrants, quadrantal angles, is that we get undefined situations. And I actually didn't draw any of the reciprocal ones here, but it happens with the reciprocal functions as well. So let's say we wanted to try and figure out, for example, cosecant of 0. Well, it's going to be the reciprocal of sine. Since sine was 0 over 1, that would be 1 over 0. So that would also be undefined. But I'm not going to go over all the reciprocal ones in this video. Okay, and then finally, here's the unit circle, which I kind of showed in one of the animations before. There's 2 approaches to trigonometry, the right triangle approach and the unit circle approach. I'll say in this series of videos, I kind of focused on the right triangle approach, but you may prefer the unit circle approach, and that's okay too, because you can use either one throughout the course.